Hello friends, welcome to online lecture series of Engineering Mathematics 2. Today we will continue with our topic gamma function, and we will see the next property of the gamma function. So let's start with the definition of gamma function. We already know the gamma function definition. If the integration goes from 0 to infinity, e raised to minus t, t raised to n dt is nothing but gamma of your n plus 1. So we will just see the next standard conversion of your example. If the index of your exponential function is not minus x, it is in the form of minus k times x, then how to just find the solution of such a example? So first, when we compare the definition of your gamma function, the value of index of exponential function is minus x or minus t. We already saw the gamma function is not depends on variable. The variable is a matter in gamma function. So the example is given here. Evaluate integration from 0 to infinity x raised to n minus 1 e raised to minus kx. So we have to just first assume the given particular example is equal to some letter and is equal to I. So I equal to integration 0 to infinity x raised to n minus 1 e raised to minus kx. So when we observe this example, the index of your exponential function is minus kx. So we have to put the value of your kx is equal to some new variable. Suppose the value of your kx is equal to t. Then we have to find the value for x. So x equal to t upon k, a simple conversion. Then we have to differentiate this particular with respect to any variable. So derivative of your x becomes dx and the derivative of your t becomes dt, and k is constant, it remains as it is. So the value of your x is equal to t upon k. Therefore the value of your dx is equal to dt upon k, and the limit of your integration remains same. When x is 0, the value of your t also 0. X equal to infinity, the value of your t equal to infinity. So we have to change the variable of the integration. So we have to change the value for x. X is nothing but t upon k. So value for x is replaced by t upon k, and the index of your x is n minus 1. So we represent this particular integration goes from 0 to infinity t upon k, whose index is n minus 1. And the value of your kx is t, so e raised to minus t, and the value of your dx is dt upon k. We have to just make the separation of the numerator and the denominator. So the index of your t becomes n minus 1, and 1 upon k, whose index becomes again 1 upon k, whose index becomes n minus 1. E raised to minus t as it is, 1 upon k as it is. Then we have to just add the index of your 1 upon k. So when we add the index of your 1 upon k, it becomes 1 upon k raised to n, which is constant outside the integration. Then we have to just write the remaining terms as it is. When we compare this example with the definition of your gamma function, the index of your t is n, so the answer is your gamma of your n plus 1. Here the index of your t is n minus 1, so we get gamma of your n, and index of your k is n, so we got gamma of your n upon k raised to n. In simple manner, we said that if the index of your exponential function is minus kx and is getting multiplied with, suppose, x raised to n, its answer is gamma of your n plus 1 upon k raised to n plus 1. If we change the integration of your x, we change the index of your x, that is x raised to n minus 1. So we get the answer of this particular example is gamma of n upon k raised to n. With the help of this property, we can find the solution of some examples. When we see example here, evaluate integration 0 to infinity x raised to 4 e raised to minus 5x dx. When we compare this particular integral with the gamma function of this, the value of your n is equal to 4 and the value of your k is equal to 5. So we say that when we replace the value of your n is equal to 4 and value of your k is equal to 5, we get gamma of 4 plus 1 upon 5 raised to 4 plus 1. And we know that 4 plus 1 is equal to 5. So gamma of 5 divided by 5 raised to 5. Again, gamma of 5 is nothing but 4 factorial divided by 5 raised to 5. And 4 factorial, its value is 24 and 5 raised to 5 is 3125. In a similar manner, we can find the example in different index. When we compare in this example, the value of your n is equal to 3 and the value of your k is equal to minus 1 upon 2. So replacing the value of n is equal to 3 and k is equal to 1 by 2, we get a solution gamma of 3 plus 1 upon 1 upon 2 raised to 3 plus 1. Gamma of 4 upon 1 plus 2 raised to 4. Again, gamma of 4 is nothing but 3 factorial and 1 upon 2 raised to 4 becomes 1 upon 16. Finally, we get the answer 6 upon 1 upon 16 is equal to 96. Again, when we see this example, the n is equal to 3 by 2 and k is equal to simply minus 1, or k is equal to, we say that 1. Replacing the value for n and k, we get a solution in the form of 3 root pi upon. In this way, we can find the solution of the example by using standard properties. So let me see another example if the index of your exponential function is other than minus x or minus variable. This is the another example. The index of your x is 2 upon 5 and index of your e is minus 6 times x. So the value for n is equal to 2 upon 5 and the value for k is 6. Replacing in the formula, we get a final solution, that is. The next example, evaluate integration 0 to infinity x raised to 9 e raised to minus 2x square. So in this example, we have to assume first I is equal to this integration. When we observe the index of your exponential function is minus 2 times x square, so we have to replace this value with another variable. So put 2x square is equal to t. Then we have to find the value of your x. So the 2 is multiplied to your x square, it becomes divided by 2. So x square is equal to t upon 2, taking the square root on both the sides. So x equal to root t upon root 2. When we change the limit of your integration, x equal to 0, t equal to 0, x equal to infinity, t equal to infinity. And lastly, we have to just replace the value. We have to find the value for dx. Dx, derivative of your x is dx. 1 upon root 2 is remains constant. The 1 upon root 2 is constant. We have to just say that 1 upon 2 is constant. We are replacing 1 upon 2 here. And the derivative of your root t is 1 upon 2 times root t and dt. Multiplying the numerator and the denominator by root 2. So 2 times root 2 into root 2. We get root 2 dt upon 4 times root t. This is the value of your dx. We can write in this form also. So change the variable of your integration, putting the value of your x and value of your index of your exponential function. This is our given example in which we have to change the value for x equal to root t upon root 2 and whose index becomes 9. This is the value of your x. and index of your exponential function is 2x square, and we have to just put the value of your 2x square is equal to t, and value of your dx equal to this. Then we have to just make the separation of your indices. So root t and root 2 is nothing but index 1/2. So it becomes t raised to 9/2, 2 raised to 9/2 separately. And making the conversion, we will take this dt outside for simplification. Then we have to add the index of t. Root 2 is constant, 4 is constant outside your integration. 1/2 raised to 9/2, 9/2 is also constant outside the integration. Again, t raised to 9/2 remains here. And t raised to half is also remains here. We have to add these two index, 9/2 minus 1/2. Taking the value of your t raised to half in your numerator, it becomes t raised to minus half. And just comparing with the definition of the gamma function, we get the solution of this example. That is gamma of 5. And we know that gamma of 5 is nothing but 4 factorial. 4 factorial upon 64, we get a final answer 3/8. In a similar manner, you can try for this example. Thank you.